In the last lecture, first we talk about the phonoresonance. Okay, this is a very important physical concept. Okay, so everyone knows that if we only has one resonator, okay, only has one resonator, we have Lorentz shape, special line. The A means the amplitude of the mode. Okay, Lorentz shape. The A also can be represented about extinction cross section or absorption cross section or some kind of things. Okay, so you can see if one resonator, okay, so when they couple to the free space, they produce a Lorentz shape. Okay, this is I think is the most case for some application, some antenna or something. Okay, by the way, in last lecture we learned the phonoresonance or phonospectral. Compared to the Lorentz spectral, the phonospectral is asymmetric. Okay, it's asymmetric. It's asymmetric. Okay, it's a sharp change. Okay, there's typically has 0 point due to destructively interference. Okay, so it has a quite different feature compared to the Lorentz shape. Okay, this is a phono shape. I hope everyone should remember its shape. When you see the shape, you can remember the physics. Okay. For the phonoresonance, typically we have the two kinds of coupling can produce the phonoresonance. One is a discrete state, okay, or discrete eigenmode, like a cavity mode or waveguide mode or kind of thing. Okay. Photonically, so we can understand it's in defect. When you introduce defect, you can produce cavity mode. Like grating, it has some guided mode, so it's a discrete state, and then they couple to the interference with the continuum or like a free space. It's a very broad band. Another is just a narrow band dark mode. Okay, I mean this mode cannot be excited plane wave, except this mode coupled with bright mode. Okay. The bright mode has a broad band because initially the bright mode can be coupled to this free space, so it has a leaky loss, so it has the bandwidth that has a wider than the narrow band. Okay. When the two kind of situation, they can produce a phonoresonance. Okay. So the first case. Okay, for this, I think the standard case is grating. Okay, everyone know the grating can support some guided mode. Okay, in the grating. Okay, so when you plane wave to illuminate this grating, the coordinate phase matching condition can be satisfied. I mean, K0, sin theta, 2 pi over p m equal to the real part of propagation constant. The beta is a propagation constant of this guided mode. Okay, it's a propagation constant.
P is the propagation, right?
Yes. This is P. This is the propagation constant. Okay, the beta here is a complex number because due to the leaky loss. Okay, beta is a complex number. Okay, due to the leaky loss. When this happens, the excite guided mode. When the guided mode is excited in its grating layer, okay, the guided mode also leaked out. Okay, also leaked out. Okay, due to the reciprocal theory. Okay. Then they can interference to an incident wave. Then so their reflection or transmission spectrum show some phonospectrum. Okay, this is the first case. This is a discrete state. It's interference with the continuum. Okay, this is a very standard case. Okay, another is just bright mode to the couple mode. Okay, this is the monopole coupled to the dimer. Okay, when the E field is vertical polarized. This is a monopole element is polarized something like this. The positive with negative. There's a dipole moment here. Okay, due to attractive Coulomb force. Okay, it has attractive Coulomb force because there's a low. So it has negative and positive charge along this dimer. Okay, so this dimer is called this couplable mode. Okay, when they are very close to each other, they can be coupled. That means they have a spectral and spatial overlap. This is important. When they are very far from each other, they have no spatial overlap. Maybe there are some resonance frequencies are very far from each other. There is no final resonance. Okay, so it means they need a spectral and spatial overlap. Okay, then they can produce a final resonance. Okay, another concept to produce resonance is just symmetric breaking. Okay, because
do you mind to go back into it?
huh?
Do you mind to go back into it?
Go back.
Some question for the dark mode we said in last lecture is you said it cannot be excited directly. You have to fully
Right.
mode. So it's a mode is one of the final resonance, one kind of dark mode, right?
What's the say again?
The final resonance is one kind of dark mode. Is that right?
No.
Because
Yes,
that final
yes,
resonance
no,
also
no,
cannot
this
be
concept.
directly excited, right?
No, this concept. This final resonance is just spectral line. The spectral line can be happen in bright mode, also can be happen in dark mode.
You mean the final resonance?
Yes, exactly. It is spectral line.
But last time you told us that the
No.
final resonance cannot be excited directly. You have to put the slide.
Right. But when you excited, sorry, it has not.
You have the slides that say that last lecture.
Let me to draw this.
And also the continuum probably you have to clarify to student. Because there are two kinds of continuum we talk about. One is the frequency domain. One is the
Okay, forgot that. This quantum optics is too difficult for that. Okay, you cannot understand. Okay, actually, it's too difficult. Okay, I mean, continuum is you can understand in free space. Or they are very broad band. It's continuing. Okay. Maybe in chapter 5, I'll talk about this.
This is the
Okay, you can see what's the feature. Okay, the feature is here. When they coupled, okay, they has final resonance for this bright mode. Also has, because it's lossless, it's not significant. It's lossy. It also has final resonance for dark mode. Not just dark mode. Or this is.
I understand that all of them can be exist, but if you go back to previous slide,
Maybe.
this one.
Okay.
You said that the existing of the mode is one thing. Whether we can excite it is another thing.
Right, exactly. So mode is here. It's bright mode and dark mode. It has many modes for the electromagnetic system. But when they're very close, they can couple. If they do not couple, they have no final resonance effect.
Final resonance is one kind of dark mode.
Not what's the meaning of one kind of a.
It's final resonance.
No. Final resonance is destructively, constructively, or broad. Is a wider, okay, bright mode and coupled to a narrow dark mode. This is the definition.
Say again.
It's a constructively or destructive interference between the wider bright mode and the narrow dark mode. Okay, this is a condition. Or just I can remove this. It's a wider resonance coupled to narrow. This is standard definition. You can read this. Okay, this is bidimensional. Okay, final resonance is a constructively destructive interference. This is the first thing. This will be interference. Another is narrow discrete resonance and a broad spectral line. All continuing. Okay, this is a definition.
So if that's true, that means that either dark mode or the bright mode have to be.
Yeah, dark mode, bright mode is just one situation. Satisfy this basic because the dark mode is narrow resonance because there are no radiation loss. Okay, and this bright mode, because this bright mode has a radiation loss, so it has a bandwidth is much larger. It's larger than the dark mode, so it's broadband. Okay, this is a feature.
So dark mode is one kind of mode that totally bounded inside the object. It cannot be radiated. It doesn't have actually outside the boundary. Right?
Use plane wave. This person use plane wave. They cannot excite it if without this mode. Like couplable. If for sphere or something, they have the couplable mode. You cannot excite it. Okay, let me explain this to you. You can see if a sphere, right, it has dipole. If a metal sphere, when you use E field, they can be excited very easily because they are matched. Okay, they are polarization. But for sphere, they also has another kind of mode. Okay.
Not this one.
Right, something like this. They also have this kind of mode, but they cannot incite, right? E field. Okay. Why they cannot incite? Because they have some polarization issue. They have so first thing you can say they have symmetry. This is sorry.
Okay, you're right, this one.
Right, they cannot be excited easily. Some modes cannot be excited easily. So okay. I use this case better because I talk about this. Okay. For this case, why they have symmetric breaking? For initially something like this. There has some mode. This is called dipole. This is dipole mode. They can be excited by the E field because they match. But the E field cannot excite this so easily because the net dipole equal to 0 is callable. They cannot excite. Okay. And this coupling also very weak. Okay, very weak. Because this net dipole is non-zero, the net dipole is 0, weak. So people do a symmetric breaking. Okay, to make this spectral and spatial overlap. Okay, to make this coupling is possible. To make this final resonance. So this is something we talk about this.
So one more question back to the previous slide, if you don't mind, go there. You also mentioned to students that there is typically the modes that the profile typically we use Lorentzian distribution. But if you know, but I told you, I asked you last lecture, some people they will use Gaussian to describe modes field distribution.
Not the modes.
You say not quite often because it's the same concept.
First is not the modes.
But if you look at the manual,
Gaussian is for the local density of state. It's not.
No, let me finish it. If you go to some catalog of laser, and also fiber optics,
yes,
they use Gaussian distribution to describe the field profile of.
This is field profile. Mine is not field profile.
Yours is a frequency domain.
Right. This is not a field profile. This is extinction cross section or amplitude. This is quite different thing.
Okay, I see.
Yeah. This is typically only has two kinds of this. Okay. Gaussian is a field profile is another thing. It's a spatial distribution. Okay. This is just a response at a frequency like extinction cross section, scattering cross section. Kind of thing.
So Sha Wei, for final resonance, the circuit model you propose that can always be those two resonators. One example is the bright mode and the dark mode.
Yes, this is because this is a bright mode. It has a leaky loss. This is a dark mode. No leaky
so
loss.
if I throw away this model, then can I say that the final resonance because it's due to the interaction between two modes?
Due to the
What's your throughout?
Throughout this circuit model, in the general statement, final resonance is because of the interaction between two modes.
Yes, but if the two modes are both bright mode, they cannot final resonance. This is very important. If a plane wave can excite some maybe dipole mode, also plane wave can be excited some high order mode simultaneously. When they are coupled, they cannot final resonance. It's just hybrid. Okay, it's a quite different thing. So this is very critical. Here is a resistance. Here is no resistance. It's something.
So that is what I just try to address. That the dark mode actually don't have a loss. The dark mode is because you don't have R.
Another thing you can also dark mode. This is initially. This is original final resonance. For plasmonic, this situation is more complicated. Here, the loss is larger. Because they have ohmic loss and leaky loss. Here they only have ohmic loss. This is for plasmonic.
So we still can have loss.
We still can have loss, but their bandwidth is different. This is very important. It's bright and narrow. Okay. Or else they cannot have final resonance. If the bandwidth is almost comparable, it cannot be resonant. Final resonance. So this is original definition is very accurate. It's narrow discrete resonance. It's a broad spectral line. Okay. This is a very standard definition. You must satisfy. Okay, even in microwave, you satisfy this. I also believe it has a final resonance.
Yeah, in microwave, possibility exists a lot in the filter theory.
Right,
you
maybe
create
this a lot.
We call zero, transmission zero. The transmission zero is due to the two-mode interaction. And actually, you could control and generate high-order zeros on both sides of the resonance.
In microwave, when they talk about
also for
wideband, how wideband is it?
It could be wideband, could be narrowband, depending on how you control it.
How to control?
Also, to continue the wideband actually is not that wide.
Yeah, not this just comparable. It's wide.
So they give different name. You could butterwall which does not have 0, and you have Chebyshev, you have the 0. You can convert the transfer between them even with the same type of filter.
So how do you define the case for exciting the photoresonance in microwave?
Also, you excite from one side, you receive it from other side.
Well, but in the requirement means
Right.
The split has a continuum. Is also follow the same concept, or that?
First thing, you must see this spectral line.
This is the spectral
This is spectral line,
line.
something like
Yeah,
this.
This is you can see.
we could see this type of spectral
Okay,
line,
that's possible.
but my point is more than that. We could have another 0 on the other side if
Oh.
we want.
Oh, okay. But if I have another 0, this symmetry is not final resonance.
Right, so it's more than that. I can have this pattern.
Okay. So it's double photo resonance?
I don't know.
You can see it?
No. If it also has a final line, it's a symmetry, it's not final resonance. Final resonance is asymmetric.
So at the end, whether you get it is from this kind of amplitude and the omega brought together to get the distribution.
Right. People just Dao said in microwave we did not draw Newtonian cross section, scatter cross section for scatter. We just draw transmission or reflection because there's some guided wave structure. It's guided with a filter. There's some way you go here, these transmissions and reflection. We draw that. We also maybe can see something like
If
this.
you can see something like this, you can help it.
Right. If you can see something that no one said is final resonance, then
Not
you can understand it's a culture paper. I think it's very good work. It's because you can connect the different knowledge in different
That's my
fields.
point. You actually can find the similar
Yeah.
format.
That's very interesting. So this is something we talked about in last lecture. Another we talked about the source. Okay, source. Source. Okay, surface enhanced Raman scattering. So I think the most important thing for source is a spectral. Okay. Oh, sorry. So fluorescence. If for fluorescence, the spectral something like this. This realization go down. This go up. Realization. Okay. So this spectral. So this spectral is a broadband, okay? It's fluorescence, very intensity. Okay. But for this fluorescence is very difficult to check what's called fluorescence. Okay, this is a fluorescence. Fluorescence is a resonance process. I mean, all the transition just real atomic level. It goes to real chemical realization, then to the emission and realization again. Okay, you can see every transition is a real. Okay, this is a real atomic or electronic state. They call the resonance process. So fluorescence. So the source is different. Raman scattering is different. The Raman scattering, it can do the virtual level. It's a ground state to here. This is a virtual level. This is a virtual level. Okay, then can emission down. Okay, this is called it's a Stokes shift. This is Stokes scattering, or maybe something can be anti-Stokes.
What is virtual level?
And
what is virtual level?
This is a virtual level. It's not a real.
How can you get it?
Yeah, they can get due to some nonlinear feature. Okay, you can understand it's a nonlinear harmonic oscillator.
Two-photon absorption.
Yeah, but not two-photon absorption. This is second harmonic generation. Second harmonic generation, they have omega, the two omega, right? So this omega, and this omega, I draw this. Let me draw this better to clarify this. This is very important. This is called Stokes. This is called anti-Stokes. Let me draw this anti-Stokes. Okay. This is a virtual level. Well, how about the second harmonic generation? Second harmonic generation. Someone studied this. I studied this recently. If this is a real level, okay. Maybe that real level is something here. This is virtual. This is virtual. This is omega. This is omega. the emission 2. This is a pure scattering process. Scattering. Or nonlinear scattering process. No absorption. Okay. No very strong absorption. Why? If you do a resonance case, if I do this, I go to the back. If I jump to real electronic state realization here, every state at a real electronic state, they have a very strong absorption. Okay. Here is virtual level. I do this virtual level. Okay. This is real level. Let's go. This is a real. This is a real. This is a virtual. Okay, when I do the virtual level, that's typically the absorption is weak. It's just nonlinear effect. You can understand this nonlinear harmonic oscillator. I mean, harmonic oscillator is Kx. They have a Kx square term. They have nonlinear feature in the material. And omega, the emission, they give omega, another omega, they emit 2 omega. Okay, this is also a virtual level. Okay, that's Raman scattering. Raman scattering is a non-resonance process. Okay, it's non-resonance, typically it's non-resonance process. So the signal is very weak.
So all of them are serious?
Yeah.
Not just the left-hand side one or the right-hand side one?
Right-hand side is the second harmonic generation, no serious. But this is second harmonic generation. Second harmonic generation and the third, they are non-resonance scattering. Okay, but the third, you can see this is a shift is very small. Here is omega, 2 omega, this is just. This is second harmonic generation. Okay, so this is a similar. It is just jump to a virtual level, not a real level. It's a non-resonance, so their need enhancement is very weak. Okay, so
if I absorb 1 photon, I give you 2 photons out, it's also second harmonic.
Yeah. If you give the
1 photon in, 2 photons.
You said it's a reverse process.
Yeah, reverse process.
Reverse process is also called second harmonic generation. The second harmonic process. Okay, not generation. But typically, we did not consider the return back because we consider omega, 2 omega is stronger. 2 omega go to omega is weaker. Typically,
no, it's very hot topic. Down conversion.
Yeah, down conversion is worse. Yeah, it's much weaker.
This is up, the other is down, right? So it's it's not that real. You can see
it's the Raman scattering. It's weak. Okay, it's very weak. Okay, so they need EM enhancement. In last week, we know that we can enhance. It's a factor. Enhanced factor is proportional to E over 4 squared. Okay, because they have 2 double resonance. One is for the incident wave, another for its scatter wave. Okay, you can see this gap. You put this molecule within the gap. It has light. It's incident. So first thing, they are excite the surface plasma to enhance. Another, because they has can be seen a dipole. The Raman scattering emission can be seen a dipole, many dipole. This dipole also excite the surface plasma and go out. So this is a double enhancement. So finally, we know it's E over 4. So if you can enhance 100 times, you finally enhance 10 times. So it's a very strong enhancement. Okay. So this is something we learned in the last lecture. Okay. So this lecture, I talk about some new thing. Okay. What happened? Oh. Sorry. I don't know what I touched about this.
Well, we can go to the bottom and switch to the other one.
Yeah, okay. Okay. Today we talk about this metamaterial. This is final part for this plasmonics. We talk about metamaterial and images, okay, and perfect imaging. Okay, it's metamaterial. It's a very hot topic. Even though it's still a very hot topic, we call it metamaterial. Okay. So the material has typically has 4 different category. Okay, one degree is means epsilon is larger than 0, mu is larger than 0. Here we ignore the loss like this. Okay, this is a traditional, this is a conventional material. Okay. Everyone knows this. Okay, then we learn this epsilon smaller than 0, mu larger than 0. Okay, it naturally exists, right? It naturally exists. It's a metal at visible light. Okay. It's a metal at visible light. Okay.
Well, visible can be epsilon can bigger than 0, right?
No.
No, visible.
No.
Or at least. Oh, okay, I see. At visible light.
Yes, at visible light. Silver, gold. Okay, we call it a single negative. Okay, or single negative. Single negative material. Okay. There's another material, so mu smaller than 0, epsilon larger than 0. This is possible. Also naturally exists. So magnet. They also call it single negative. Okay. Until now, okay, I feel the 3 parts, right? They are naturally exist. They have some example, but only has 1 part that not feel, because they are naturally that not. Until recently, they cannot find this material. The real material has this property, but effectively they have this. They can achieve. Okay, if epsilon 0, mu is 0. Okay, this part we call the metamaterial. Because this cannot be achieved in a real world material. They only can be achieved by some equivalent or effective permittivity. Okay. Let me go through this. Sorry, it's not right. Plasmonic part 2. Go down this. Okay, so I should use full screen. Let me see this. Okay, this is important. Okay. You can see this part we call double negative. The refract index here is a negative. Refract index is negative. You can see this. This is a red and the purple line is an incident wave and the reflective for energy flux. Okay, for energy flux. You can see here it's a conventional material. Okay, the incident wave. The wave can be penetrated to this material typically. So they has a refraction. Okay, it has a certified Snare law, right? Snare law. Learn this. Okay. For this plasma, as I said, because epsilon is smaller than 0, the K is the pure imaginary part. So it's a decay. It's a bulk material, they will decay. So it's totally reflective and decay is up. Okay. So this is a metal. Okay, something. The metamaterial you can see, if n is negative, because epsilon is negative, mu is negative, so n here is also get this negative sign. Okay, you can see here is at the same side, right? Because n1 because sine 1 theta 1 over sine theta 2 equal to n1 over n2. This is Snare law. Whenever n is negative, is positive, so sine theta is just reverse direction. Okay. Another thing you can see here. This is a very interesting picture. The red line is energy flux for this. This epsilon equal to -1 mu to -1. This is energy flux. Okay. This is for the phase. Okay. You can see the phase. This is k vector. I mean the propagation direction in the metamaterial. Okay, is reversed with this energy flux. Okay, because the n is negative. Okay. So here, this is a very interesting phenomenon. Okay. So this is a wave propagation is reverse on the contrary to the direction of energy flow. Okay, this is a feature we call it as a left-handed metamaterial because this is a k vector. It's a k vector here. It's a reverse. Okay, reverse. reverse or I mean originally EHK they have used right-handed because EH and K they have right-handed. Now EHK is left-handed. Okay, so they call it left-handed material. Okay, so this is the reason. Okay, so what's the definition of metamaterial? I copied this from Wiki. I think this is the definition to go. Okay, metamaterial is a smart material. Okay, they call smart material has a property cannot yet be found in nature. That means you cannot find a bulk material has epsilon smaller than 0 and mu smaller than 0 simultaneously. Okay, no, this kind of bulk material has this property. Okay, so metamaterial has their property not from the material, but from the design structure. Okay, this is important. It's a design very special structure. That means these typically metamaterial are inhomogeneous, like some periodic structure, or this is some inhomogeneous. When you see this inhomogeneous structure as a homogeneous media, okay, or use the effective media theory, you can see it's a homogeneous media. This homogeneous media satisfies this relationship, epsilon smaller than 0 and mu smaller than 0 effectively. Okay, so this shape, geometry, size, orientation, arrangement, okay, you control this, can give this smart property, okay, to control electromagnetic wave. So why people is so excited about this metamaterial? Because they can block, absorb, enhance, band the electromagnetic wave as you want. You can control that very easily with this metamaterial. Okay, so this is the benefit. It go beyond. It's for the possible with the conventional material. Okay, so this is kind of important. So first thing is that is everyone should know this anti-flow and this propagate and the K direction they are reversed. So they call left-handed because the K, EH and K they has from left-handed left-hand rule. Okay, not right-hand rule. Typical. Okay, they call the metamaterial because the N here is negative. Okay, so this has this very interesting refraction. Okay, so at microwave. Everything at the PEC, okay, people how to realize this effective, okay, realize this some material has an effective epsilon smaller than 0 or some effective mu smaller than 0, okay, that means effective, okay, not this material itself. Typically in microwave, every material can be see a PEC. You can see this is a wire, this is a metallic wire line, this is split ring, everything a PEC, okay. But when you see this structure, this is the periodic structure, it's a magnetic wire line. You see this line as a homogeneous media. Okay, this is homogeneous media show this single negative feature. Okay, that means epsilon smaller than 0. Okay, epsilon smaller than 0.
What is PEC?
PEC, perfect electric conductor. Okay, called PEC. So let me talk about the first case. What happened? Okay, why? How to achieve epsilon smaller than 0 at microwave frequency? This is by the Pandry. Okay, they use a metallic wire. Why use the metallic wire can be achieved this feature? Everyone knows this is a benefit from the metal material. Everyone knows the Joule model. You learn the Joule model. I teach you the Joule model for metal and the visible light, or not visible light, it's for metal. Okay. So this 1 minus omega p square, omega square is epsilon omega. Okay. So from this equation, we know that if omega smaller than omega p, if omega smaller than omega p, the epsilon is negative, right? And so omega p determines which kind of frequency band it has a negative feature. If omega p is very high, it only can be achieved in a visible light regime. It's difficult to achieve this. So what's the omega p? Omega p is a plasma frequency equal to n e squared epsilon 0 m effective math. Okay, this is called plasma frequency. Okay, omega p here. So if you want to achieve the epsilon small and 0 at a microwave frequency, you must decrease omega p to the microwave range. Okay, if omega p is 10 gigahertz, okay, it's very good. They can have a feature in. But typically for metal, rare metal, this omega p and visible light is something of regime. Okay, so Patrick the idea from this equation how to reduce omega p. Okay, reduce omega p to a microwave regime. So n here, you can reduce n. You can increase effective mass, right? This is the basic idea. Okay, so they use Y. Why use Y? Y is very sparse. Okay, when you homogeneous media, this very sparse metal, the homogeneous, the density will be reduced. When you see the homogeneous media. Okay, so this is one feature. Another is the Y is very thin, the inductor is very light. If they have an inductor, when you increase the self-inductor, they just increase M. Why? Why increase the self-inductor, they can increase M. Everyone to know this analogy. Okay, this analogy is very important. It's about the harmonic oscillator theory. Okay, let me to set this equation to you. Everyone know this harmonic oscillator. It's a rainbow. M dx over dt plus tau dx over dt plus m omega 0 square x equal to some maybe driven force, if have some force. Okay, this is a spring ball model. Okay, everyone know this is kx. Okay, this is acceleration. Right, this is a friction. Thermodynamic damping something. Okay, this we learned that. But you know, this is very analogous to circuit physics. Right? You learn this R, C, R. Yeah. You will find this certified the same. It has maybe voltage source. It's a L, C, R. Okay. Everyone know the KVL or KCL, chemical current couple. You can draw this. Okay. So let me draw this if I remember clearly. Okay. And it's a C, it's a du, over dt equal to I, right? I'm right. L di over dt equal to V. Okay. So to the KVL, you know, L di over dt, right? This is a plus u just 1 over c integral I, right? No problem. It's a u for this okay capacitance, and plus Ri equal to V, right? No problem. This is just a KVL. L di dt equal to V. I do I over C. I do the integral, right, from z to 0 to t, or minus, right, is I to V. Okay. So here, if I make this I equal to dq over dt, everyone know that charge. We'll see what happens. It's very magic. dq dt. Okay. Right. R dq dt. 1 over c q. Right. Okay. This is something powerless. You can see. It's I with dq dt to do the integral to the derivative of q. Right. So analogy. L is m, right? Inductor is effective mass. R is a fraction. Okay. C, 1 over c is just k, L. So capacitance is similar to the spring, like a K, spring constant. Okay, similar to this concept. So L is similar to the mass or inertia. Why is very analogous? Remember the physics? If you take the train very fast, and you suddenly stop the train, people just throw out. They call inertia, right? Like L, if there has current go to this circuit, and you suddenly change to maybe open this circuit, the current still go further, right? Still go further due to some Faraday law, right? It still go further. It's similar to L. So L is similar to L. So increase L, increase M. Okay? So they use a very thin line, wire line. They use very thin wire line. They increase the self-inductor, they increase effective mass. Okay? It's fully unmanaged. The increase the effective mass, they reduce the density, finally reduce omega p. Go to a microwave frequency. Okay, this is the simplest idea. Okay. So finally, they can achieve this negative incident omega. Okay, this is by the Pendry. It's a very classical paper. Initially, they published in Physical Review letter. Okay, they achieve the effective plasma frequency around the gigahertz. Okay, and this structure is non-resonating structure. It's non-resonating. Another insight when you see this structure, you can see this structure. You see the structure. It's a small gap, right? This gap similar to waveguide. Similar to waveguide. Well, this waveguide has a cutoff. The mass higher frequency, they can transparent, and lower frequency, they are totally reflected back. So this is a plasma feature. Higher frequency for metal, they are transparent. Lower frequency, they are opaque. So it's similar to waveguide. Okay. So you can see this another insight. So this is for Pendry's work. When they published the paper, several authors write a comment on to him. Don't believe this result. Write a comment on. Okay, to against these results. Okay, you can see the original. And finally, several years ago, verify that Pendry is right. Pendry did not reply that. Okay, this is very interesting. This is pioneering in the field. Another is split ring, also by the Pendry. They published in IEEE MTT. Okay, split ring. Okay, split ring is a resonant structure. As I said, this is a capacitor. Because the capacitor has a large common area. Okay, it's the capacitor between here. The inductance is about this. Okay, line. Okay, this is a split ring. Okay. So at the resonance frequency, if omega smaller than omega LC, LC is a resonance frequency. If the incident frequency is smaller than the resonance frequency, the induced dipole is in phase. Okay, in phase of excitation field. Okay, in phase. For increase of frequency, okay, this is the current start to lag of the driven field. Okay, that means it cannot follow this driven field. It's out of phase. Okay, it's out of phase. Okay, so in this field, the metal material is diamagnetic. What's the meaning of diamagnetic? That means it's similar to a loop. I give a top view. Okay, when I give an H field, they produce a current H induced. They are reverse incident. This is incident field. Okay, like give an incident field, they produce a current to cancel this incident field. Okay, to cancel the incident field, induced field. Okay, this is split ring. This is positive, this is negative. This is Pendry's idea. So this out of phase. If out of phase is diamagnetic because they produce currents cancel the incident field. Okay, so they are called diamagnetic.
It's always, or you have to satisfy something.
This should be out of phase. Should be larger than the frequency, larger than the resonance frequency. This is in phase. In phase is a paramagnetic. 顺磁, sorry, paramagnetic. In Chinese it's called 顺磁. Okay, paramagnetic. Diamagnetic is 逆磁. Okay, diamagnetic. Okay, maybe it's a technical word. I mean they produce current. This current produce a reverse H field with original field. They call it diamagnetic. Okay, so at this very small region, you can see this at a frequency region just above. Okay, just above the omega LC, the effective mu. The effective mu is smaller than there. Okay, smaller than there. Because at this frequency, first thing, the resonance is still very strong. Because they are not very far, right? Resonance strong. So they can produce a very strong induced H field to cancel this direction. Okay, cancel the original H field. So they make this mu is negative because they reverse the sign of H. Okay. Like mu equal to B You can understand mu equal to B over H, right? Equal B over H. Okay, they reverse the sign of H because this reverse current can reduce that. This can make this mu has a negative. Okay, it has strong resonance. This is the resonance structure. Okay, this is
I believe the circle ring structure, is it have some open region or is just like due to drawing defects?
this is open.
Yeah.
This is open because there's no current. The current only has
They intentionally make it, right?
Huh?
I think intentionally make this kind of opening.
Yeah. If close, they cannot have this feature because the C capacitance is between the here and is no capacitance here. They must make this current reverse each other. This current come here, this current come here. Okay, this is must do that.
But if you want to have current like that, if you make it open, then how can the current flow?
Right. This is displacement current. You know,
Oh.
like a parallel plate. Parallel plate very close to displacement current connect this.
The displacement current is at the open region of the ring or
Right, between this region, has displacement current from here, the displacement. So they have, you can see, they have two parallel plates. You have displacement current go here, go down, go here. It's the reverse direction. Okay. So this if go here, this displacement current go here, go here. So you can see this and reverse current, like a ring. It has reverse current.
So how about the opening ring? I mean the open region of the open.
What's the word open region? I mean, even this region?
No.
Oh, this
I mean,
region.
yeah,
No current. No current. It's very small because the capacitance is very large. Capacitance is very small. It's
If I make it close, what happens?
it makes it close. You know,
One
cannot
of the
manage
ring, for example, if you make the internal ring close,
close.
yeah, it's not an open ring, it's a closed
I
ring.
think it's
Why do they have to do that?
it has a quite difference. If you make this can be resonator, you know.
Yes,
it can be
yes,
resonator.
yes.
They're not good. Because this resonator, the LC circuit depends on the C between this loop and the L is here and here. This is the idea. If you close, this can be a resonator. It's not good.
Oh,
You're very complicated.
so you have to have these open to get the error, right?
Right. L is this part,
Yeah.
the circle, and plus this part, this L part. The C part is between the common area between here. This is LC circuit, something like that.
And
Okay.
and also the opening direction can it both.
Yeah, this is very cool. You can rotate, but feature is different. You can rotate. They have different feature, but they can control the polarization. They can rotate. Yeah, someone
It
rotates.
still can be passed as
Right.
material.
They can be better material, but the response is quite different from this curve. Okay, they can rotate that. So it's very interesting patterns. This is the resonance structure. Okay. So basic idea is just to give the edge. Okay, insert the edge in here. They produce a reverse edge. Okay. They produce current give a reverse edge. This reduction can be cancelled. This original instant edge just flip the sum of the edge to make the mu effectively small and zero.
So the inside, let's take a look to the inside circle. When have a field popping in,
Yeah.
the inside circle.
This is quite complicated. This inside, outside also coupling.
I mean, yes, that's the point. Then the inside circle have this way to against the incoming field.
Right.
At the same time, the outside circle also
Net, you know, net.
Okay.
Net. So the net is something like this. You can understand. It's very complicated. I cannot explain very detail. But it's a net. It's a magnetic momentum can flip out.
The net of the two rings.
Right. Net of two rings can flip.
Oh.
Okay. So this out. So they make the mu is small and zero. This is original idea. Okay. So I just give this to maybe I have no time. Yeah, because this is commonly used in the microwave frequency. You can see this is a metallic wire. It's similar to the electrical dipole. This is another inside. It has a positive charge. It has a negative charge. Okay, because it's truncation. This is electrical dipole. This is split ring. Split ring because current is something like this. Due to Ampere's law, you can see that they are similar to magnetic dipole. Similar to magnetic dipole, right? You have to do this magnetic dipole, something like a loop. That's magnetic dipole. Okay. So you can use the complementary structure according to Barminian principle. Okay. This electric dipole can flip to the magnetic dipole. The magnetic dipole can flip to the electric dipole. You can see we can use the complementary structure. Okay. This is the fully complementary structure. So the first, this is also pioneering in science. Okay. 10 years ago. Maybe 10 years ago. It's by the David Smith group. Okay. They put this metallic line okay, a metallic wire and a split ring together. Because metallic line, they can achieve the epsilon small and zero effectively. The split ring can achieve the mu small and zero effectively. So they pull them together. Experiments pull them together. You can see this split ring. Here you can see it has metallic wire. They pull them together and do this isotopic. You can see different orientation. Make this isotopic. They can achieve this negative refraction index. This first paper published in Science.
What material do you say again? Magnetic or metallic or
Metallic.
metallic?
PEC, everything
Okay.
PEC. Okay. But they do a substrate. You can see they have substrate. Hold on. Make this isotopic. Okay. This is by this concept. Okay. Okay. So this last picture, I finish this and I can close. Okay, this is a common use of left-handed metamaterial and optic regime. You can see this. Okay, this is a two plate. This is interesting because it has a displacement current. You can see that reverse. It current from here, due to evanescent coupling, we can do here, then go down and go up. Okay, this is a circular loop. It's a circular loop. Okay, it has circular loop here. Okay. Because this is very close to each other, they have evanescent coupling. Okay. If for microwave, it's very difficult because maybe this area is not large enough. Sorry, I think this record is cannot very realized in microwave or in optics. They can form this loop current can form a magnetic dipole, and this E field here they can form an electrical dipole. Okay, this E field electrical dipole. This loop current is magnetic dipole. This is reverse current. So I draw this picture. This is metamaterial. Okay, this coupling by the evanescent, it has some evanescent wave coupling. Okay, when evanescent wave coupling, it has something like this. Okay, so this has a current reverse each other, so it has a magnetic dipole H in here, and an electrical dipole, maybe something in here. So they can do the metamaterial. Okay, this is the experimental result and the simulation. You can see at this very small region, the N can be small, this is 0, can be small and 0, this small region. This is first experimental demonstration and optic regime by this structure. This is so I think class is over. I have no time to finish all the part. Okay.